Well, hello AP Stats students. Mr. Eicher here, bringing part 2 of a lesson about using the binomial distribution and approximating it with a normal distribution. I got this question from my friend Luke Wilcox, the stats medic. So thank you, Luke, for this question. Let's dive right in. This quote is from Luke, who says, "My daughter Reese always picks out all of the cherry starburst as soon as we open the bag. This is not acceptable. So now she is required to take a random sample." Sounds like a stats teacher. A bag of starburst candies can be considered a simple random sample of the whole population of starburst candies. Since there are 4 uniformly distributed flavors, the probability that each starburst is cherry flavor is 1 out of 4. Each bag of starburst contains 200 candies. Suppose we buy 1 bag of starburst. Let the random variable x equal the number of cherry flavor starburst candies in the bag. Question 1. Is this a binomial distribution? To be a binomial distribution, we have to satisfy 4 things, and the abbreviation we use is bins. So first, do we have a random variable that has binary outcomes, and we'd say yes, the candy that is selected is either cherry or not cherry. Right? We have x is the number of cherry flavor, so we can count either yes, it's cherry, or no, it's not cherry. Next, are the events independent? Well, we'd say we have 200 candies out of the whole population, and we're taking a simple random sample. So 200 candies is less than 10% of the population of starburst candies. So even though we're sampling without replacement, if we're sampling without replacement, we really don't have independent events, but we could ignore that as long as we're not taking a huge part of the population. And we're not. 200 is definitely less than 10% of all starburst candies in the world. Next, n, the number. Is there a fixed number of trials? We do have a fixed number. N is 200 candies in a bag. And then lastly, s, do we have the same probability of success? And we were told that there's a 1 in 4 chance that we would get cherry. So our p is 1 in 4. So p is 1 out of 4 and n is 200. To calculate the mean and standard deviation of x, I'd encourage you to pause the video and see if you remember the formulas to calculate the mean x for a binomial distribution and the standard deviation x for a binomial distribution. The mean formula is n times p. That's 200 times a quarter. So that should make sense. The mean is 50, and the standard deviation formula is npq, where q is 1 minus p. So that would be 200 times a quarter times 3/4. So our standard deviation is approximately 6.12. To interpret the mean of 50, we would say, in many bags of 200 starburst, we expect on average 50 cherry per bag. So remember, the mean of a random variable is known as the expected value. So we like to use the term expect in here. And we also like the law of large numbers. So this is in many, many sets of bags of 200. The average per bag will be 50. And then to interpret the standard deviation, thinking of what we just interpreted with the mean, we would say, in many bags of 200 starburst, the number of cherry typically varies from the mean, 50, by 612 starburst, cherry starburst. So important terms there. Standard deviation, we talk about typically varying from the mean. And again, we have, this is in many, many bags of 200 starbursts each. Next, let's answer 2 questions about binomial probabilities for review. Question 5, what is the probability of getting exactly 60? The probability of getting exactly 60. Our random variable is x, the number of starbursts out of 200 that are cherry. And we want exactly 60, so equal to 60. We showed earlier in number 1 that it's binomial, so we'll use the binomial theorem or the binomial formula, where n is 200 and p is a quarter, our cherry. So we would have this equals 200, and we're choosing 60, 0.25 to the 60, 0.75 to the number of failures, which is 200 minus 60, so 140. The other way you could see this written, instead of the C notation, you could see it written like this in choose notation: 200 choose 60, 0.25 to the 60, 0.75 to the 140. And there is a button if you didn't want to type that all out. That's binom PDF, P for one particular value, where n would be 200, p is 0.25, and x is that exact value of 60. Calculating that, we get a probability of 0.0171. Is the probability of getting exactly 60 cherry flavored starburst. What is the probability of getting at most 60? So that's the probability that x, if the most it can be is 60, that means 60 and everything below that. So that would be a less than or equal to 60. When we have an inequality like this, it's best to use binom CDF. So this would be binom CDF, where n is 200, p is still a quarter, and x is still our boundary of 60. And using binom CDF, not binom PDF, we get 0.9546. That's very, very high probability, right? The mean is 50, so you'd expect on average to get 50. So 60 or less is getting 0, 1, or 2, or 3, or 50, or 51, 52, 53, all the way to 60. So it makes sense that the probability would be very likely to get at most 60. And then the last part, we will redo problem number 6 with a normal distribution. And to do this, we need to check our condition. We'll call this our normal condition, or our large counts condition. Normal condition. So n is 200, p is a quarter. That would be 50, which is greater than or equal to 10. So that works. And then the complement of 25, 75, that would be 150. And that's also greater than or equal to 10. You do have to check both. So since both are greater than 10, greater than or equal to 10, we can approximate the distribution with a normal curve. And earlier in the question, we had calculated the mean and the standard deviation. The mean we found was 50 from above, and the standard deviation we found was 6.12. And we just checked the condition, a normal condition. So problem 6 is the probability that x is less than or equal to 60. So we can have a normal curve. The mean is 50. The standard deviation is 6.12. And 60 is close to 2 standard deviations away. So I'm going to put it way over here and less than or equal to that. So to calculate this, we would be calculating the probability that z is less than or equal to 60 minus 50 over 6.12. Using the normal CDF command, we get an answer of 0.9489. So with our normal approximation, we get an answer of 9489. The actual answer, the exact answer, is given by the binomial function, which is 9546. So we were about a half of a percentage point away from the answer. But the important part is for you to understand to be able to approximate a binomial distribution with a normal distribution, this normal condition or large counts condition has to be met. If that condition isn't met, then gradually your normal approximation will be farther and farther away from the exact answer, which is what binom CDF gives you. If you've made it through this video, kudos to you. Give me a thumbs up if you actually see me giving you a thumbs up. Have a great day. Thanks for watching the video. See you next time.